Hi everyone, I'll be doing some questions as a review for the MAS 117 final exam. So there are 6 questions in total. It should take around maybe an hour or two or so for the video to complete. So let's get started with the first question. Suppose that the temperature at a point xy on a metal plate is given as T equal to 4x squared minus 4xy plus y squared. An ant walking on the plate traverses a circle of radius 5 centered at the origin. What are the highest and the lowest temperatures encountered by the ant? So what information are we given in this problem? So let's take a look. Okay, so we are told that the temperature on a metal plate is T equals to 4x squared minus 4xy plus y squared. And that the ant is traversing a circle of radius 5 centered at the origin. So this will give us information about the path that the ant will have to take. Then we want to know what are the highest and the lowest temperatures encountered by the ant. So the question gives us some function that describes the temperature and some condition that this ant needs to follow. So this is an optimization problem. And in this course, the technique that we've learned to solve optimization problems is the Lagrange multiplier technique. So the Lagrange multiplier requires an objective function and a constraint function, or multiple constraint functions if possible. In this case, our objective function is t of x and y. Because that is the function that describes how the temperature varies on this metal plate. Then what is the constraint? The constraint is given in this second statement that I've highlighted, that the ant traverses a circle of radius 5 centered at origin. So the ant can only move along this circle. And what is the circle? So we know that a circle is, of course, r squared. Well, let's do this in xyz. So x squared plus y squared will be equal to 5 squared, so that's 25. So that's a circle, and that's the only path that the ant can walk on. Then we'll use that to find the highest and lowest temperatures encountered by the ant. So once we have the critical points, because the Lagrange multiplier technique will give us the critical points, we can then substitute them back into the objective function to evaluate the temperature, and then from there we'll find what the minimum and the maximum temperatures are that the ant will encounter. So let's get started. So we have, I'm just going to write it here again in case I have to scroll up and down. T of x and y, our objective function, is equal to 4x squared minus 4xy plus y squared. Then our constraint function, so we're going to call this, say, g of x and y, will then be x squared plus y squared equals to 25. Because remember, we want our constraint function to be in the format of g of x and y equals to some constant c. So we'll leave the 25 there. Then from the Lagrange multiplier technique, we know, let me change colors, that the gradient of our objective function, so grad t, will then be equal to some constant, so some Lagrange multiplier multiplied by the gradient of g. And then we know that g will have to be equal to c, the constant. So what does that mean in terms of setting up the problem? It means that we will have 3 equations and 3 unknowns. So our 3 equations are, so let me write this out, partial derivative of t with respect to x equal to lambda partial g partial x, then partial t partial y equal to lambda partial g partial y. Then our last one is, of course, g equal to c. So these are our 3 equations. Our unknowns are lambda, x, and y. So then if we start populating and actually doing the derivatives and forming our equation, so I'm going to put that down here. So partial t partial x is equal to 8x minus 4y, and that will be equal to lambda times, so partial g partial x is 2x. So that's equation 1. I can also write this, I'm just going to divide it throughout by 2. And I'll make it in terms of lambda. So lambda equal to something. So I'm just going to move to divide everything throughout by 2x. That will give me 4 minus 2y over x. And I'm going to call this 1 prime. Equation 2 becomes, so it's the partial derivative of t with respect to y is minus 4x plus 2y, lambda, and then 2y. So it's partial g partial y. And again, I'll write it in terms of lambda equal to something. So that will be minus 2x over y plus 1. And I'm going to call this 2 prime. And lastly, our third equation, I'm just going to put in what g is. So that will be x squared plus y squared equals to 25. And that would be 3 prime. Now, the reason that I made equations 1 prime and 2 prime be lambda equals to something is because I can then equate the two. So then I can make equations 1 prime and 2 prime equal to each other, which would then allow me to solve for, or at least express x in terms of y or y in terms of x. Either one works. So let's do that. So I'm going to make 1 prime equal to 2 prime. I can do that because they're both lambda equal to something. So that will be 4 minus 2y over x equal to minus 2x over y plus 1. Okay, so if I expand this out, I'll multiply both sides by xy. So let me change colors so that you can see. So I'm going to multiply everything by xy. And that will give me 4xy minus 2y squared equals to minus 2x squared plus xy. Then I'm going to move everything so that they're going to be on one side. So that will be 2x squared plus 3xy minus 2y squared equals to 0. So that's a quadratic. And I can solve this quadratic. And that will be 2x minus y times x plus 2y equal to 0. So now I have x in terms of y, so there are two possible values. So x can either be equal to y over 2 or minus 2y. So two possible solutions right now for x. Then what I need to do is to take these values of x and substitute them into equation 3 prime to solve for y. Once we have y, we can then solve for x. We don't actually need to know what lambda is. We don't really care. So let's look at the first case where x is equal to y over 2. Then 3 prime becomes, so that'll be y squared over 4 plus y squared equals to 25. So I'll multiply both sides by 4. So that will give me 5y squared equals to 100. Y squared will be equal to 20. So y would be plus minus 2 root 5. So then if I substitute that back in, that means that I will have x equal to plus or minus root 5. So for the first value, I have two possible solutions. So I have root 5 and root 5 and minus, sorry, 2 root 5. Minus root 5 and minus 2 root 5. So two values that we'll check later. We'll check them once we have everything. Then let's look at the case where x is equal to minus 2y. So what I'm doing right now is I'm finding the values of x and y that correspond to the critical point. Because the Lagrange multiplier technique gives us the critical point or critical points of our objective function subject to our constraint, which means that these are either the minimum or the maximum of our temperature function, given that it's along the path of the circle. Okay, so then let's substitute in x equals to minus 2y into equation 3 prime again. So that will give us, so minus 2y squared, that's just 4y squared plus y squared equals to 25. So that's 5y squared equals to 25. Y will then be equal to plus minus root 5. So then x will be equal to minus plus, because there's a negative sign in front of 2y. And that'll be minus plus 2 root 5. Which means that our possible solutions are 2 root 5 minus root 5 and minus 2 root 5 and positive root 5. So we have 4 combinations. So we'll check each and every one of them. So we're going to check all the xy coordinates that we found. And of course, if the value is lower, that will be the minimum value. And if the value is higher, then it will be the maximum value. So let's look at t root 5 and 2 root 5. So let's take a look up here. So that will be 4x squared minus 4xy plus y squared. So that will be 4 times root 5 squared minus 4 times root 5 times 2 root 5 plus 2 root 5 squared. And that is, that's 20 minus 520, 80. No, 40. 5, yeah, 5 times 8, 40. And then plus 2 root 5 is, that's also 20. So that is 0. Then let's check the negative of that. And this will also be the same because the negative signs will all cancel out. So that will also be equal to 0. You can check this, but they all cancel out. So it means that at these 2 points, we have a temperature of 0. So that will be our lowest temperature. I don't think we're going to get anything lower than 0. So that's our minimum point. So now let's check the other point, which should be the highest. If not, I'll have to erase this and change it. So 4 times 2 root 5 squared minus 4, 2 root 5 times minus root 5 plus minus root 5 squared. So that will be, so that's 20 times 4, 80, plus, that's a plus. So that's 5 times 8, that's 40. Then root 5 squared, that's just 5. So that is 125. And then just to be sure, we'll check the negative case as well. And it'll get the same we'll get the same answer because the negative signs are just flipped, but the way the objective function is formulated, it cancels out. So this means that this will be our highest temperature. That's in our domain. So those are our 2 solutions to the problem. So let's double check that we've answered the question. Okay, yes, we have. We found the highest and the lowest temperatures that are encountered by the ant. The lowest temperature is 0 degrees, and the highest is 125. If you have, say, if you have more than one constraint, then you have another constraint function. In that case, your objective function will be a function of 3 independent variables, so x, y, z. So you'll have another constraint, so another Lagrange multiplier to solve. And we've done a few examples of that in class. So you can refer to that, and there's some questions in the textbook if you want to do more practice. Okay, so let's move on to question 2. So question 2 states that we have a circular lens of radius 2 inches, and it has a thickness of 1 minus r squared over 4 inches at all points r from the center of the lens. So find the average thickness of the lens. So in this case, our lens will look kind of something like this. So that's our lens. So that'll be our origin, and that'll be some radius r. And the thickness will vary. So our thickness will vary. Thickness, I'll call thickness t, will be equal to 1 minus r squared over 4. So that will vary radially. And we want to find the average thickness of the lens. So to find the average quantity, we'll take the sum of the quantity over all the points and divide by the, in this case, the area. So what does this translate to? It translates to, if we want to find the average thickness, So I'm going to put a bar on top to denote the average. So average thickness will then be equal to 1 over the area of the lens times the integral, the double integral, over our domain, or our region, of the thickness function, which is a function of r, then integrated over the area, the region. So that's how we find average thickness. So this is a double integral question. So we need two things. We need to evaluate the double integral, and we also need to figure out what is AD. Now with AD, you can either, technically it is just integrating 1 over the domain. But in this case, because we know that it's a circular lens, and we know what the radius is, we can actually take a little shortcut. Since it's a circle, we know what the area of circle is. This is pi r squared. So pi r squared in this case will be 4 pi. So we know what the area is. If it's a shape that's not regular, then you would need to do the actual integral. But in this case, because it's a circle, and the question is not really asking you to do the integration for the area, you can just use pi r squared. But to integrate the thickness, we're going to need to actually do the integration. So in this case, we have a circle, radius r equals to 2. And we'll need to evaluate our double integral. So t dA. So what would our limits of integration be, and what would the order of it be? Since it's a circle, we should most likely use polar coordinates. You can use Cartesian coordinates, but it's going to be a bit more work. When it's a circle, we can use the polar coordinate. So how do we describe our circle of radius 2 in polar coordinates? Well, that function will just be r equals to 2. So this means that when we do our integration, we will then be integrating. So we'll start from the origin and out to the radius, which means that we are going to go from 0 to 2, right? So that will have one line. And then to complete this entire circle, we'll then turn that line, or rotate that line from 0 to 2 pi. So theta will be from 0 to 2 pi, and that will draw out that circle. Remember, we don't care about the thickness in this case because we know it's a circular lens, and thickness is just a value. It's a function value. So that's our function value. So we don't, like, this is not a 3D problem. This is a 2D problem. So then we can substitute in our limits of integration. So 0 to 2 pi, then 0 to 2. So we'll substitute in what is t. T is 1 minus r squared over 4. Now, when we do integration in polar coordinates, do not forget that there's an r, dr, then d theta. So we'll bring in that r. We can also integrate the theta separately because there's no dependency on theta in r. So r does not depend on theta. So we can bring that integral out. So that becomes r minus r cubed over 4 dr. So this is because r does not depend on theta, so we can separate the integral. If r depends on theta, we can't do this. But in this case, we know in the limits that r will just go from a constant value to another constant value. There's no dependency on theta inside the function, so we can do this and it's fine. So that will be, so that's 2 pi out there. Then let's do the integration. So we have r squared over 2 minus r to the 4 over 16. And we are going to evaluate that from 0 to 2, which will then give us, so 2 pi times, so 2 squared. So we can ignore the 0 because everything will be 0. So 2 squared, that'll be 2 minus, so r to the 4 is 16 as well. So that's 1. So that will give us 2 pi. But we're not done yet because we only found the integral here. We're still, in order to evaluate the average thickness, because that's what the question wants, the average thickness will then be, so 1 over AD times that integral that we just evaluated, which should then be, if I'm just bringing in all the values, so I have 4 pi and 2 pi, so that'll be 2 pi over 4 pi, so that's 1/2. So this is our answer. The thickness of the lens, the average thickness of the lens is 1/2 inches. So in this case, you have to first recognize how to compute an average value when you have the value described by some function over some region, whether it's a plane region or surface region or a volume region. Know how to do the integral, and then put everything together to get your average value. All right, so let's take a look at question 3. So in question 3, we want to find the volume of a solid in the first octant bounded by the sphere rho equals to 2, the coordinate planes, and the cones phi equal to pi over 6 and phi equals to pi over 3. Okay, so let's look at the question. The solid is in the first octant. And it's bounded by the sphere rho equals to 2, the coordinate planes, and then the cones. So by coordinate planes, this means that it will be, the coordinate planes are x equal to 0, y equal to 0, and z equal to 0 planes. So those are the planes that the coordinate planes refer to. The first octant, so when you split your Cartesian coordinate system in 3 dimensions, the first octant is the one where all the values are positive. So x is greater than or equal to 0, y is greater than or equal to 0, and z is greater than or equal to 0. So all 3 of these cases must apply. Then it's also bounded by the sphere, so the sphere is straightforward, and the cones. So now we're given 2 cones. Phi equals to pi over 6 and phi equals to pi over 3. So let me draw out what this cone, what these 2 cones will look like. Let me switch colors. So, okay, the first cone will look something like this. Excuse my drawing. So that's cone number 1 with some angle there. So that would be phi equals 2. So this will be the smaller angle, pi over 6. Then the second cone will be something like this, where this angle out here will be phi equals to pi over 3. So then the region that is between the two will be this region right there. Imagine that region in 3 dimensions. I'm not going to draw the sphere on there because it's going to get really busy and messy. But imagine that there's another sphere there, and that will enclose everything. And the sphere will have a radius of rho equals to 2. And we want to find just the volume. So volume, so just the integral. So volume to solid will be the triple integral. Let me rewrite integral sign. So that'll be over our volume region, dV. So then we need to figure out what our limits of integration are, and then do the integration. And in this case, given that we have a sphere and a cone, we should probably do this in spherical coordinates. So that will simplify things down quite a bit. So let's use spherical coordinates. And we should do this because all our information is already given in spherical coordinates. Well, at least the main information. We can convert the information about the octant and the coordinate planes into spherical coordinates quite easily. So what information do we have? I'm just going to summarize down here. So we have a sphere, and sphere of rho equals to 2. We have 2 cones. Phi equals to pi over 6 and phi equals to pi over 3. And we've already shown that what that area will correspond to. Then we know that it's going to be bounded. It'll be bounded in the coordinate plane, so the positive ends only. So in the first octant, so positive values are x, y, z only, and that we're going to cut it off at x equals 0, y equals 0, and z equal to 0. So z equals to 0 will be our lower bound, x equals to 0 will be our lower bound, and y equals to 0 will also be our lower bound. So we're going to cut that off there. So then, okay, so how do we limit our volume to be in the first octant? So when something is in the first octant, we need to think back into what is the definition of rho, theta, and phi in spherical coordinates. Say I have some point that's defined in spherical coordinates. So that's my point there. Make this a big dot. Okay. This length here gives me rho. The projection of rho, so the angle that this projection makes right there. So the angle that rho makes with the x-axis, let me do that first. So let me backtrack a bit. So the angle that makes there, that's phi. Then, if you were to project rho down to the xy plane, so that will make that will be a right angle triangle there. This line that you project down, let me switch colors. So that's another line that you project down. So you looked on the top down. So the line that you project down will have a length of r corresponding to the radius in cylindrical coordinates. And the angle that R makes with the x-axis right there, that will be theta. So if things are limited in the first octant, it means that phi will have to be above 0, which in this case, it will be. We don't have to worry about that. The second restriction is on theta, because rho doesn't have a negative value, so rho is just a distance, right? So then we need to restrict theta such that our points will only be in the first octant. And how do we do that? We would then have to restrict theta to be, so let me draw this again. So x and, sorry, let's use, okay, so x and y. And then if that is our point, the projection, that's r. And then this is theta. So to restrict theta to be in this zone only, we would then have to restrict theta to only values between the range of 0 and pi over 2. Because remember, the x-axis is theta equals 0. What corresponds to the y-axis would then be theta equals to pi over 2. So we'll have to restrict theta. Okay, so then what does that all of this translate to? So rho will be between 0 and 2. That's our limits of integration on rho. Phi will be between pi over 6 and pi over 3. That's already given by the geometry. That's the restriction. And then theta will be between 0 and pi over 2. So those are our 3 limits of integration on each of the independent variables in spherical coordinates. So if we put everything together and make sure that we are integrating in spherical coordinates, we will have, so we'll put the limits on phi last. That will be, we'll go from pi over 6 to pi over 3, then theta, so 0, pi over 2. So rho will be between 0 and 2. Then the differential operator dv in spherical coordinates becomes rho squared sine phi, d rho, d theta, d phi. In this case, like the previous question, there is no dependency on theta in any of the terms. So we can actually bring out the theta integral as a separate integral. We'll need to keep, oh, I don't have space. So we'll need to keep the other two together because they are present in the integrand. So there. So rho squared sine phi d rho d phi. Okay, so let's do the integration. This becomes pi over 2. Well, we'll integrate rho first. So I'm just going to bring the limits on phi down. So integrating rho, that gives me rho cubed over 3 from 0 to 2. Then sine phi d phi. So that's 8 over 3. I can bring that out as well. So pi over 2 times 8 over 3. That's a constant, so I can bring that out. Then the integral of pi from pi over 6 to pi over 3 of sine phi d phi. This becomes 4 pi over 3. Then integral of sine phi is minus cos phi from pi over 3 to pi over 6 to pi over 3. So that's 4 pi over 3 times. Okay, so cosine of pi over 3 is 1/2. So minus 1/2. Then cosine of pi over 6. So minus minus, that becomes plus. Cosine of pi over 6 is root 3 over 2. So this becomes, I'm going to bring the 1 over 2 out. So this becomes 2 pi over 3 times root 3 minus 1. So that's our volume of that region. So this question, the tricky bit is figuring out what the limits of integration are when we have shapes that are not, say, something that you can kind of easily visualize. So you might need to sketch it out. Okay, so moving on to the fourth question. Suppose that a particle moves through the force field F equals to xy times I plus x minus y times j from the point 0, 0 to 1, 0 along the curve x equals to t and the y equals to lambda t times 1 minus t. For what value of t will the work done by the force field be 1? So lots of information that we're given. So we're given a force field. So that's the equation there. Now we're told how the particle is moving because we have a particle moving. So what point to what point? We're told what is the curve. Then the question is asking us to determine what value of lambda, because the curve is in terms of lambda. So what value of lambda will the work done by this force field be 1? So lots of things. Okay, so how do we parse all this information? So let's first look at, okay, so we have a particle that is moving from a force field of xyi plus x minus yj from the point at origin to some other point, 1, 0. But we're already given the parametric curve for it. We have the parametric equations here. X equals to t and y equals to lambda t times 1 minus t. So we'll need to substitute x and y from our parametric equations into our vector field. So we need to do that. Then, because the question is asking, what is the value of lambda when the work is equal to 1? So we'll need to find the work given the force field. And we'll find, from there, we'll have an expression to compute the work, equate that equal to 1, then solve for the lambda value that will make that true. So we need to find work, let work be equal to 1, then find lambda. So work will be in terms of lambda first. We'll find lambda to make that true. So that's what we need to do in this question. Okay, so the first thing we're going to need to do is to convert, well, first, what is work? Work is the line integral of a force field over some curve. So that's our work, and we want this to be equal to 1. Now, what is f dot dr in terms of our parameter? So we'll need to convert f dot dr into to be in terms of a parameter t. So dr will then be, so that will be a vector of the derivative, so that will be x prime t dt, and then y prime t dt. So that's converting dx dy into in terms of dt. And then f, so we want this to be in terms of t instead of x and y, so we'll have to substitute them in. So that will be x is equal to t, so t times lambda t 1 minus t times I, and then plus t minus lambda t 1 minus t times j. So that will be equal to, I'm just going to write this in vector notation. So lambda t squared 1 minus t. Then t minus lambda t 1 minus t. So it's f, and that's dr. So f dot dr will give us our new integral. So work will then be equal to the line integral of lambda t squared 1 minus t, and then t minus lambda t 1 minus t dot, so x prime t, that will be just 1. So that will be dt, comma. So y prime t, that will be, okay. So that will be lambda minus 2 lambda t dt, which is c. And then, so if I do the dot product, that will give me, so I'm going to factor out dt for the whole thing. So lambda t squared 1 minus t plus t minus lambda t 1 minus t times lambda minus 2 lambda t close parentheses dt. So we'll expand this out and evaluate the integral. But we haven't determined what the limits of integrations are. So what's the limit of integration? We know that the particle is going to move from point 0, 0 to point 1, 0. So let's take a look at our parametric equations. So for the point 0, 0, it turns out that if t is equal to 0, then we will get that point. Okay, so then what would the point 1, 0 be? We just base this off the parametric equation for x. So that would be t equals to 1. That would give us the point 1, 0. So that will be our limits. Okay, so I'm going to substitute that limit in. So integral will be from 0 to 1. And I'll expand all of this. So that will be lambda t squared minus lambda t cubed plus lambda t minus 2 lambda t squared minus lambda squared t plus lambda squared t squared plus 2 lambda squared t squared minus 2 lambda squared t cubed. All of that integrated with respect to dt. Okay, so let's I think we can simplify this down a little bit more. So let's take a look. That becomes lambda t squared minus lambda t cubed plus lambda t minus 2 lambda t squared minus lambda squared t. Okay, we can add these two up. So that becomes 3 lambda squared t squared minus 2 lambda squared t cubed dt. Okay, so let's actually do the integration. So that will be lambda t cubed over 3 minus lambda t to the 4 over 4 plus lambda t squared over 2 minus, so 2 lambda t3 over 3 minus lambda squared t squared over 2 plus, so this becomes lambda squared t cubed minus, so that'll be lambda squared t to the 4 over 2. Evaluate this from 0 to 1. The 0 limit is nice, so then I don't have to evaluate that second one. And then 1 just means that I substitute 1 into everything, so that's also nice as well. So then I will get lambda over 3 minus lambda over 4 plus lambda over 2 minus 2 lambda over 3 minus lambda squared over 2 plus lambda squared minus lambda squared over 2. Okay, so a bunch of these terms cancel out. Okay, so that cancel out. And then if we add everything up, so that will be, okay, so this can go away, and then the 2 becomes a 1. If I add everything up, that gives me minus 3 lambda plus 6 lambda minus 4 lambda over 12, which means that is minus lambda over 12. So that's our work. That's the value of work in terms of lambda. Then we want the case where lambda will give us work of 1. So then we'll make, to find what value of lambda would be, so that'll be negative lambda over 12, so that's our work, equal to 1. So it turns out that lambda will be equal to minus 12. So that's how you would solve this problem. So in this question, once you know how to set things up, and a lot of questions in this course is once you know how to set things up, the execution is not the difficult part. It's the setting up that's the difficult part. Once you know, okay, so what is work? How do you get that? How do you convert everything into our parameter t, set up the limits of integration? Doing the integration is straightforward. It might be a little tedious in this case because there are a lot of terms, but a lot of them also cancel out. Even if you have a quadratic, you can still solve for possible values of lambda if that's the case. In this case, we elect out, and there's only one possible solution for lambda. So once you know how to set things up, the rest of it is pretty smooth sailing. Okay, so 2 more questions. The fifth question is we want to determine whether our vector field e to the x cos y I minus e to the x sine yj is a conservative vector field. If so, find a potential function for it. So this is a 2D case. This is in R2. We are given a vector field. And then we want to find the potential function for it. We need to check whether it's conservative or not. This is in R2. So in R2, for a vector field to be conservative, the following statement needs to be true. Partial p, partial y should be equal to partial q, partial x. This is p, this is q. So let's first check if the field is conservative or not. If it's not, then the question becomes very short. So check for conservation. So partial p, partial y, that will be the partial derivative of e to the x cosine y, which is e to the x, minus e to the x sine y. Then partial q, partial x. So that's negative e to the x sine y. And that is just negative e to the x sine y. So therefore, partial p partial y is equal to partial q partial x. So f is conservative. So if f is conservative, then f is equal to the gradient of some function f, lowercase f, which means that that p will give us, so this means that p will then be equal to the partial derivative of lowercase f with respect to x, and q will be equal to the partial derivative of f lowercase f with respect to y. Okay, so in order to find f, we can then integrate either p or q with respect to either x or y, do a partial integration. So f, x and y, we'll just use p because it's the first one. So p dx. And p is equal to e to the x cos y, so dx. So we're going to integrate that, and that will give us e to the x cos y plus, in this case, some g of y. So we need to put the constant there because we are doing an indefinite integral. There are no limits of integration in this case, which means that what we know is when we do the integration, this is the integration with respect to x. We don't know that whether there are other terms that depend on y or other constant terms present or not. So we need to add this g of y term in there as a placeholder to help us, to let us know that, okay, there is a potential term that is there that is either a function of y or just some constant that we still need to determine. So we're not done if we just do the integration because we need to know this is a partial integration with respect to x. We still need to know if there is terms that are dependent on y or not. Because when you take a partial derivative of terms that only depend on y, but take them with respect to x, those terms go away. They go to 0. So we need to find what, if they are those terms and what they are. So we need to find what is g of y. So I'm going to scroll down a little bit more. Okay, so we need to find g of y. And we do this by taking the partial derivative of this answer. So we're going to take the partial derivative of f of x and y, lowercase, with respect to y. So e to the x cos y plus g of y. And this term will have to be equal to q from our vector field. It needs to be equal to this q term. Why that's the case? That's the case because that's the definition of what is the conservative field. Capital F must be equal to grad f. And grad f is the partial derivative of f with respect to x and the partial derivative of f lowercase with respect to y as the components. So we know what those partial derivatives should be equal to. So then from there, we can figure out what is g of y. Okay, so first let's take our partial derivative. So our partial derivative is minus e to the x cosine, sorry, not cosine, sine of y plus g prime y. So that is the derivative of g with respect to y. And this must be equal to q. And what is q? Q is minus e to the x sine y. Okay, so this two terms cancel out, which means that our g prime of y is equal to 0. So what does that translate to? That translates to saying that if we were to differentiate this integration constant with respect to y, we will get 0, which means that this integration constant does not depend on y. So this means that we will have, so g of y will then be equal to some constant k, where k does not depend, k is a true constant, doesn't depend on x, doesn't depend on y. So if we put everything together, our function would be e to the x cos y plus k. So that is our answer. We won't know what the value of k is. We don't have enough information to do so. So we'll leave that as our constant, some unknown. That's an integration constant. If you have 3 variables, it's the same procedure, but now when you do the first integration, g will depend on y and z. Then we need to determine, okay, so if there's a constant that depends on only g or not, if there's a constant that depends on only z or not. And so that'll be similar to the class example that I did. And of course, if you are dealing with R3, so 3 dimensions, then the criteria for a conservative field is that the curl of the vector field is equal to 0. Okay, last question. So for our last question, we want to find f dot d double integral of f dot ds, where f is equal to 2x cubed plus y cubed times I plus y cubed plus z cubed times j plus 3y squared z times k, where S is the surface of a solid bounded by the paraboloid z equals to 1 minus x squared minus y squared, and the xy plane. Okay, so let's parse the information first. We want to find this double integral. We are given what is f, and S is a solid that is bounded by the paraboloid and the xy plane. And we're given what the paraboloid is. Okay, so let's attempt to sketch this out. I can't promise it's gonna look pretty. Well, I can't even draw a straight line, so there's that. X, Y, and Z. Okay, so we have a paraboloid. This is this one faces down. Oh boy. Okay, so the at Z equals to 0, that will be equal to 1. So that will be, so that's so that's our paraboloid. So that's Z equals to 1. And then if you look down from the top, you'll see a circle of radius 1, because x squared minus y squared, that will give us a circle. And when Z is equal to 0, x squared plus y squared will be equal to 1. So that kind of tells you what that radius will be. So x equals to 1 there, and then y equals to 1 there. Then the xy plane. So that one I'm not going to draw. So that's just xy plane is the same as saying the plane z equals to 0. That's the same. All right, so based on this, and we want to find a double integral of f dot ds. So double integral of f dot ds. This is not going to be, based on what we have drawn, this is not going to be simple to do given what f is. So how do we simplify this down into something that we can do much more easily? So then when you want to simplify things down, when you're working with double integrals and triple integrals or line integrals, you should think about the different theorems that we've learned, whether it's Green's, Stokes, or divergence. In this case, we have a surface. So there are two theorems that involve a surface. We have Stokes' theorem that relates a surface to a line integral, and divergence theorem that relates a surface integral to a volume integral. With Stokes' theorem, the double integral is on the curl of f, which is not what the question is asking. If we want to convert this to curl of f, we're going to have to do a lot of work. And that's because we need to convert what would then be the function of that will be the other vector field. Then we need to figure out what the curves are. So that's a lot of work. So let's try divergence theorem. And the good hint is that divergence theorem relates that integral that's given in the question that we want to a volume integral. So that's divergence theorem. Okay, so then if we want to use divergence theorem, what do we need? We need the divergence of f, and then we'll need to figure out what the integration limits are. So let's do the divergence of f first, and then we'll do we'll figure out what the integration limits are in a bit. So the divergence of f is equal to the partial derivative, of p with respect to x plus partial q partial y plus partial r partial z, where, this is p, this is q, and this is r. So then let's take those partial derivatives. So 2x cubed plus y cubed plus partial y, y3 plus z cubed. Okay, so let's do all of that. So this becomes 6x squared plus 3y squared plus 3y squared. Okay, so that's pretty simple. 6x squared plus 6y squared. That's not too bad if we were to integrate this, because we can also factor this out and have 6x squared plus y squared. Okay, so then next thing we need to do is figure out how are we going to integrate this. So looking at my poorly constructed drawing of the paraboloid, you can and given the fact that the base of the paraboloid at the xy plane is a circle, we can choose to do this in Cartesian coordinates, but it's gonna involve square roots and such. So I would rather avoid that. So with a paraboloid, the other option is to use something like cylindrical coordinates. Now you wouldn't use spherical coordinates because the geometry is not really a sphere. A paraboloid is more like it's more related to a cylinder than a sphere, and also then you would have to convert things into rho and all that. But just looking at the equation of the paraboloid, so z equals to 1 minus x squared minus y squared, the conversion to cylindrical coordinates is actually pretty simple, because so cylindrical coordinates are, so for those of you who forgot, r squared is equal to x squared plus y squared. Z is this equal to z. And then there's also a conversion in theta. So tan of theta will then be equal to, so it's opposite over hypotenuse, so opposite over, wait, no, it's opposite over adjacent, so x over y. Okay, so then how are we going to convert? So based on this, our paraboloid becomes z equals to 1 minus r squared. That's a pretty good hint of what the limits on z would be. So then if we were to integrate, because r would then go from 0 to 1, right? The radius of the base is 0 to 1. And then theta will just integrate to make a full circle, so 0 to 2 pi. So then z will be the one that varies depending on and the other independent variables. And then r will be between 0 and 1. And you know this because of the fact that at z equals to 0, r would be equal to 1. Then theta will be from 0 to 2 pi because we're making a full circle. Okay, so given that z depends on r, we'll have to do that integration first. Then for the next integration, so the choice is between theta and r. We would actually have to do r second, because if you recall, the conversion from Cartesian coordinates to cylindrical coordinates for a triple integral involves the addition of an r term to the expression. So there will be an r dependency there. So we'll have to do that second. And also because z depends on r, we should do that second. And then theta is just a constant. So let's put everything together in our integral. Okay, so theta will be last. So 0 to pi. R is from 0 to 1. Z is from 0 to 1 minus r squared. Then we'll need to convert this divergence into cylindrical coordinates, which is 6r squared. So that'll be 6r squared. Now the conversion is r, in this case dz, dr, d theta. There's no dependency on theta. We can bring that out, and then we'll be left with this right here. And we'll factor out the 6 as well, because that's just a constant. So I have r cubed dz dr. So that will be 12 pi out there. Integrating with respect to z first, that gives me 0 to 1 r cubed, and then 1 minus r squared dr. So that is 12 pi times the integral from 0 to 1 of r cubed minus r to the 5 dr. Integrating, so that's 12 pi r to the 4 over 4 minus r to the 6 over 6 from 0 to 1. That's 12 pi 1 over 4 minus 1 over 6. So I'll bring the 12 in. That means pi times 3 minus 2. So that will just be pi. So that's our surface integral calculated using the divergence theorem. Much simpler than trying to compute this using a surface integral with our value of f, our vector field right there. Okay, so there you have it, some 6 questions that should touch on pretty much all the units we've covered in the term. I've only chosen a few sample problems. Of course, there are other things I can test as well, but this kind of gives an idea of kind of what to expect for the final. Obviously, the difficulty of the questions in the final will be higher than what I'm showing here, but the things that you are required to compute will be something along these lines.